Good morning, my dear friends. I hope you all are doing great. And our previous topic was actually the pressure volume work. And I told you that about irreversible work in the previous class, my dear friends. And let's have a little idea. When we were talking about irreversible work, my dear friends, I gave you the expression P external delta V. That was the expression which we got. And my dear friends, I introduced a negative sign. Please remember this important point. This negative sign was introduced by me, okay, to make the work positive. If there is a work of compression, means work is being done on the system. In order to make that work positive, I have introduced this negative sign, my dear friends. So we spoke about the work of compression and the work of expansion in previous class, but both were irreversible works. So with respect to this expression, when we spoke about work of compression, our final expression was work irreversible is positive, that is work done on the system is positive. And when we spoke about the work of expansion, the work irreversible was negative. My dear friends, this was the work done on the system. So my dear friends, work done on the system is positive. Because when work is done on the system, internal energy of the system will increase. Remember that particular point. Okay? If I write down work done on the system, then internal energy of the system will increase. Remember that thing. And now work of expansion we were talking about. It's coming out to be negative. Because this negative sign was not actually in the formula. Remember that point. The negative sign, this negative sign was not in the formula, but we have introduced this negative sign so that our work will become positive when work is done on the system, and it will become negative when work is done by the system. That's why we have brought this negative sign. In previous class I have already told you. And look here, my dear friends, and work is negative. It's a work of expansion, my dear friends, and remember, work is done by the system. Work is done by the system. When system is doing the work, understand the internal energy, this stands for change in internal energy, will be negative. That means the internal energy of the system will decrease when work is done by the system because it's negative. Correct? Now, one more important point I would like to mention here. When you are compressing a gas, for this P external should be greater than P internal. Remember that for work of compression. But when you are talking about work of expansion, the P external should be less than P internal, which means P internal should be greater than this. Then this is possible. So these things we have already learned in the previous class. So my dear friends, work of compression, and this is irreversible work, my dear friends, it is positive, and work of expansion is negative. Here the work is done, okay, on the system, so internal energy of the system will increase, and here the work is done by the system, so internal energy of the system will decrease. And this compression will happen only when external pressure is greater than internal pressure. And expansion will happen only when internal pressure is greater than external pressure. I hope, okay, you have understood this thing now. And today we will be talking about work reversible, means or reversible work we'll be talking about. Both compression and expansion we'll talk about here. So my dear friends, please make note of this particular thing. Dear friends, let's talk about the reversible work, okay? First of all, this reversible work, it can be reversed. The term reversible we are writing, so that means it can be reversed. It's not taking place in just one step. Irreversible work was taking place in one step. Okay, and change in volume was very large, delta V. But this reversible work is taking place in multiple steps, and we can also call them as multiple differential steps. Small change will be there in the volume. When there's a little change in the volume, we can reverse it. So that's why we call it as a reversible work. Look here, it can be reversed in each step. If there is a little compression, okay, and due to which the volume of the gas is differentially, decreasing, means there's a little decrease in the volume of the gas, okay, then that process can be reversed. Means if we reverse the process, what will happen? There will be a little increase in the volume of the gas. So that means work of compression can be reversed by work of expansion at each step. Remember that particular point, my dear friends. So in order to understand this process, reversible work, let us take on separately the two terms here. The first term I will take it as work of compression. When we talk of work of compression, my dear friends, let us draw one diagram here. Let us suppose, my dear friends, this is P external pressure, and this is here the P internal pressure. Inside we have a gas. Let us suppose this is our ideal gas, and let us suppose we are taking 1 mole of this, and this is our cylinder. Correct? So my dear friends, what we are going to do, let us add on 1 grain of sand. This is a grain of sand. A small amount of sand I am adding onto the piston. Let us suppose at the beginning P external is equal to P internal. Okay? P external is equal to P internal at the beginning. For the work of compression, my dear friends, P external should be greater than P internal. Remember that. P external should be greater than P internal. So what we are going to do, if we add on a grain of sand here, a small weight onto the piston, what will happen, my dear friends? External pressure will increase. It will become more than internal pressure. So in step first, if we add a grain of sand on the piston, then P external will become differentially greater. Differentially means very small. Okay? Will become differentially greater than P internal. So my dear friends, in step first, if we add a grain of sand on the piston, then P external will become differentially means very little, differentially greater than P internal. So remember, when P external is greater than P internal, then the work of compression will take place, my dear friends. Yes or no? So work of compression is now possible. But you know that P external is slightly greater than or differentially greater than P internal. So there will be a work of compression. Value will decrease, but decrease in volume will be very, very little, or differential decrease in value will be there. Because external pressure is slightly greater than what? Internal pressure. Or external pressure is differentially greater than what? Internal pressure. So obviously there will be a decrease in volume now, but the volume decrease will be very, very small. We call it a small decrease in the volume, or differential decrease in the volume, or negligible decrease in the volume will be there. I hope you are understanding, my dear friends, because P external is greater than P internal. So dear friends, if we go further in this work of compression, you will find out many more things in it. So I hope you have made the note of this particular term. So I will go further. Okay. So remember, we are talking about work of compression, my dear friends. And now, till now you have understood that P external has become slightly greater than P internal. Yes? So you have understood here now, P external is greater than P internal. But I told you that P external is differentially greater than P internal. Okay? So in order to, in each step of compression, I will write down here. In each step of compression. What is the meaning of in each step of compression, my dear friends? If I add one more grain of sand here, again the piston will go little down. There will be a small decrease in volume again. If I add one more grain of sand here, my dear friends, again the P external will become slightly greater than P internal, and again there will be a very little compression. So my dear friends, in each step of compression, what happens? Remember this expression. P external will be equal to P internal plus dP, and this is basically the differential pressure. Differential pressure. We know that P external is greater than P internal, my dear friends. Correct? So my dear friends, in order to make the external pressure equal to what? Internal pressure, we have to add on a differential pressure here, a very small amount of pressure. Or you can also write it like this, my dear friends. P external. This thing can be also written like this. First of all, have a look here. We can write it like this first of all. We know that P external is greater than P internal. We can write down P external minus dP will become equal to P internal. So if we remove a little bit of pressure, a differential pressure from the external pressure, because we know that external pressure is greater than internal pressure. So that means here pressure is little bit more, and if we remove that pressure from here, what is that pressure all about? This is a differential pressure, my dear friends. Differential pressure means a very small change in pressure. If we remove it from external pressure, and this dP is because of grain of sand. If we add a grain of sand, there is a slight increase in the pressure. So P external becomes greater than P internal. But now we know that P external is greater than P internal at each step. You add on a grain of sand, P external will become slightly greater than P internal. So at every step of compression, external pressure will be greater than internal pressure. But I want to make the P internal equal to the P external. So we know that P external is greater. If we remove a differential pressure, this differential pressure is because of the grain of sand. If we remove it from the external pressure, then only it will become equal to P internal. So this thing I can also write it like this now. P external is equal to P internal plus dP. Yes or no, ma'am? That means if we add a little pressure to the internal pressure, it will become equal to the external pressure. I hope, my dear friends, you have understood up to here. So please make note of this. So dear friends, let's continue this particular thing. Remember, when we are adding the grain of sands, compression is happening, okay? So we will write down that in each step of compression, okay, there will be differential decrease in volume, that is dV, of a system. So my dear friends, dP was basically the differential pressure, and now if you look here, in every step when I am adding a grain of sand, every step there will be a decrease in volume because we are doing work of compression. Yes, and remember, such change can be reversed. You can reverse this particular change. How? If you remove the grain of sand from here, the process will be reversed. The substance will, the system will expand, but expansion will be also very, very small. Yes, if you remove one more grain of sand, expansion will happen once again. So that means this process can be reversed. I hope you have understood the work of compression. Let us go for now work of expansion. Then I will combine both of them. So let us go for now work of expansion. Remember, we are talking about reversible work of expansion. So let us understand at beginning, for example, of the process. Okay, we know that we have done the compression process for this particular system. We have compressed the value by adding a grain of sand in every step. In each step I was adding a grain of sand and value was getting compressed, but little. Now I can actually reverse that particular change. Let's have a look how. Try to understand. If we remove a grain of sand in each step, now I am removing the grain of sand in each step. Okay, what will happen? The work of expansion will take place, because when you are removing a grain of sand, what will happen? The internal pressure will become differentially, means slightly, will become differentially greater than external pressure. So my dear friends, in each step of the compression, my dear friends, now P internal will be greater than P external. So please have a look right out here and see, if we remove a grain of sand in each step, the work of expansion will take place, because P internal will become differentially greater than external pressure. Greater than external pressure, I'll mention here. So P internal is now greater than external pressure. So my dear friends, for work of expansion, now you have understood that P external is less than P internal. Okay, it can be also written as P external is equal to P internal minus dP. We know that P internal is greater. If I remove the differential pressure, yes, from P internal, what will happen? It will become equal to P external. So remember this particular expression, and remember, in each step of expansion, there will be differential increase in value. So here the value will increase, that is dV of a system. So my dear friends, I hope you have understood this particular thing. Please make note of this. So dear friends, we are talking about reversible work. Correct? And we have learned here the work of compression and work of expansion. We have learned both. Correct? So I will give an expression for the reversible work. So we have an expression for reversible work, which is W reversible is equal to negative of, this is the integration basically we are doing from VI to VF, okay, P external dV. This is an expression for the reversible work, my dear friends. We will understand this, what is it all about. Have a look. Let's draw a graph between pressure and volume here. So if we draw a graph between pressure and volume, okay, we'll get a curve like this. Okay, my dear friends. So let us suppose if we are doing work of compression, then what is going to happen, my dear friends? This will become our initial volume here, and this will become our final volume. If the change is happening, the change in volume, my dear friends, if the change in volume is happening just in one step, then obviously it will be a irreversible process. But here you have to understand that there is a change in pressure with respect to volume. That means pressure is not constant here. In irreversible process, pressure was constant. Yes. If you look here, the pressure is decreasing in this direction, and the value is, if you go in this direction, that means you are going from final to initial, which is not possible. You have to go from initial to final basically. If you look according to this, or if you go along this particular curve, you will find out this is the initial value and this is the final value. So my dear friends, the value is decreasing. When volume decreases, what happens, my dear friends? That means you are doing the work of compression. But if volume is increasing, let us suppose, that means you are doing the work of expansion. So this graph, if you look here, the initial volume is very large and final volume is very small. That means you are doing the work of compression. So this graph is for work of compression. And let me show you that the work of compression is happening in multiple steps. So my dear friends, this work of compression is happening in multiple steps, let us suppose. In multiple steps it's happening. So my dear friends, this work of compression is happening in multiple steps. Okay? First of all, if you go directly from VI to VF, then it will become the irreversible work. But we are moving from VI to VF in small steps. We call them as differential steps. These are the differential steps here. So this decrease in volume or work of compression, okay, is happening in very small steps. We call them as differential steps. I want to calculate the total change. I want to calculate the total change in the volume from VI to VF. So that's why I am doing the integration. So integration is nothing but to calculate the total change. To calculate the total change. Let us suppose here, there is a little change in volume. If we move in this direction. Little change in volume, little change in volume, little change in volume, little change and little change. We will combine all these chains. We will take the sum of all these chains in volume. And finally we will get the total volume. So if you are integrating the small things, yes or no? And the result will be the total. Let us suppose you are integrating small change in volume. And the result will be the total change in the volume. So that means integration is nothing but to sum up. Yes? So we are integrating the things from VI to VF, my dear friends. And it can be the work of compression or it can be the work of expansion. In work of compression, volume will decrease. Initial volume will be large and final volume will be small. But in case of expansion, yes, initial volume will be what? Small and final volume will be large. That is the only thing. And this work, pressure volume work, is taking place in multiple steps. And remember, if I decrease the volume here, I can increase it also. That means, my dear friends, the process can be reversed at each step. Compression, and I can go for expansion also here. So have a look here, my dear friends. If I want to write down this expression, we know that P external for work of compression, let's call it as equation 1. So my dear friends, if we have a reversible process like compression and expansion both are happening, then how will be this expression written as? Have a look here. Let us suppose for work of compression, we know already P external, okay, is equal to P internal, okay, plus dP. This thing we are already knowing for work of compression. And for work of expansion, we know that P external is equal to P internal minus dP. So my dear friends, for this reversible work, in place of P external, okay, in place of P external, I can write down P internal plus dP, or I can also write down P internal minus dP. So my dear friends, let's have a look here now. By introducing the value of P external from work of expansion and work of compression into equation 1, we get. So my dear friends, let's take the equation 1. Work reversible is equal to minus integration from VI to VF, lower limit and higher limit. So, or upper limit we can also say. Now P external, in place of P external, what can I write down? P internal plus dP for compression and P internal minus dP for expansion. So I can write down now P internal. In place of P external, I can write down P internal plus dP or P internal minus dP. So I will write down P internal plus minus dP. This P internal plus dP will give me the work of compression, and P internal minus dP will give me the work of expansion. And what is the remaining thing? dV. dV stands for the differential change in value. That value is decreasing but very, very small. Okay? So I will write down that outside, dV. So my dear friends, if you look at this particular expression, let us simplify it first. Work reversible is equal to minus VI to VF, then P internal multiplied by dV. So I will get here P internal into dV, correct? Then we have here plus minus dP into dV. So my dear friends, if you look at this expression now, this is a differential change in pressure and differential change in value. Differential change in pressure and differential change in value, yes, will be almost negligible. Differential change in pressure means small, very, very small change in pressure. Into dV, dV means very, very small change in value. So when you are multiplying two negligible quantities, yes I know, then the result will be also negligible. So I can neglect this term dP into dV. So I will write down here, my dear friends. dP into dV. Yes, correct. Okay, their value will be almost negligible because they are differential quantities. Differential means they are very, 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 very small quantities. So, my dear friends, when their value is negligible, then this expression, can I call it as equation number 2 here? dP into dV, their value will be almost negligible because they are differential quantities. So equation second will become, so work reversible is equal to negative of VI to VF, then P internal into dV. Because this term is, if you look here, dP into dV, this is a negligible quantity. So you can neglect it. This is a negligible quantity, so you can remove it, my dear friends, and our expression becomes like this. Now, let's call it as equation number 3, my dear friends. Please make note of this. So, my dear friends, by using ideal gas equation, okay, we can get an expression for P internal. So we will get an expression for P internal, that is pressure of an ideal gas. This is nothing but, my dear friends, this is the pressure due to, let's write down ideal gas, and we know that it's 1 mole only, pressure due to ideal gas. So we know that PV, that's ideal gas equation, is equal to nRT. Then what is P equal to, my dear friends? P is equal to nRT upon V. So we got an expression for the pressure, and this is pressure P internal, you can write down, because this equation is an ideal gas equation. This is our ideal gas equation, and we were talking about 1 mole of ideal gas, correct? So P internal is nRT by V. Now I will substitute the value of P internal, yes, into equation 3. Substitute the value of P internal in equation 3 we get. Let us see what we are going to get here. So if you substitute the value of P internal, that is nRT by V, in equation number 3 we get. So work reversible is equal to negative VI, VF, lower limit, upper limit, then, because you are calculating the total change between VI to VF, remember that thing. So in place of P internal now, I can write down nRT by V, nRT upon V, and then we have dV here, into dV. And everybody should know, let's call it as equation number here 4, correct? Everybody should know that N is equal to, we have taken 1 mole of a gas. R is a universal gas constant. Its value is 8.314 joule per Kelvin per mole, okay? And temperature, let us suppose this process is isothermal. So if it is an isothermal process, that means temperature is what, come on? Constant, if it's an isothermal process. So all these 3 quantities are constant. Number of moles, we have 1 mole of ideal gas, so it's constant. R is a universal gas constant. T is, let us suppose process is isothermal, that means temperature will be constant. So these 3 things are constant. So constants are not integrated because they have a fixed value. So there is no integration for the constant nRT because they have a fixed value. Okay, so let us take them out. We will get work reversible minus, take nRT out because they are constant. They are all constant. So no integration for them. So let us integrate from VI to VF. Remaining things, dV by V. Let's integrate this dV by V. Okay. So if we integrate now dV upon V, okay. So my dear friends, you need to remember here, integration of dV upon V, okay, is equal to here ln Vf minus ln Vi. So what is this all about, my dear friends? Have a look. So this is the expression with you, my dear friends. If you are integrating Well, let us suppose you are integrating dV upon V, that's equal to ln Vf minus ln Vi. This ln is nothing but it is a natural log, correct? So we'll talk about this natural log as well here. So please remember this particular expression. So let us integrate this equation now here. Let's call it as equation number 5 and we will integrate it. Please remember this information here. So our expression is work reversible is equal to minus nRT, then integration of dV by V. So my equation was work reversible is equal to minus nRT, then integration from Vi to Vf for dV upon V. That was my equation number 5. Okay. Once we integrate it, my dear friends, have a look. You will get ln Vf minus ln Vi. ln stands for natural log. So you will get work reversible is equal to minus nRT. Then here you will get ln Vf minus ln Vi. So that is the expression, that is the integration of dV upon V. So after getting it, you need to remember one more expression here, my dear friends. Remember that log A minus log B is equal to log A upon B. So let us consider this as log. This is natural log only. Log A minus log B. So this expression will become now work reversible is equal to minus nRT log A minus log B. Log A minus log B is log A by B. So I will get log. This is which log? Natural log. What is A here? Vf divided by Vi. So my dear friends, this is our expression now here. Let's call it as 6. And remember one more thing. This ln stands for natural log. ln is nothing but a natural log. Okay. This natural log can be also represented by its equal to log to the base e. And this e is known as Euler's base. Okay. And its value is 2.7. Okay. Now this natural log I am talking about here, ln stands for natural log. If you want to convert this natural log into the log to the base 10, its expression is like this. ln is equal to log to the base e. It's also equal to 2.303 log to the base 10. So remember this thing. Natural log ln is equal to log to the base e. It's equal to 2.303 log to the base 10. So when we know this expression, in place of this ln, I can write down now 2.303 log to the base 10. So once again, ln is equal to 2.303 log to the base 10. So have a look here, my dear friends. Work reversible is equal to minus nRT. Then in place of ln, we can write down 2.303 log to the base 10. 10 is not required here, but you can mention Vf upon Vi. So I can take this term in the front. I'll get work reversible is equal to minus 2.303 nRT, then log to the base 10 Vf upon Vi. So that is the final expression for the reversible work, my dear friends. I hope everybody has understood this thing. So this was all about the reversible work. I have combined the work of expansion and work of compression. And this process was taking place in multiple steps. Yes, and in each step, if there is a compression, and that compression can be reversed by the expansion, which is possible, because change in every step was very small. So finally you have gotten your expression, that's work reversible is equal to minus 2.303 nRT log Vf by Vi. Please remember that and have a great time.